Well, thank you very much for that warm introduction. I'm going to be talking about Rust for JavaScripters. Show of hands, who has heard of Rust before? All right, cool. Looks like no one raised their hands, as far as I could tell. All right, but first, a quick bit about me. I'm Sean Grove, coming out of San Francisco. I work at a company called OneGraph, but I won't really talk about that today. I'll give a little bit of context about my experience with Rust. The main project I shipped in Rust was a cross-compiled ARM embedded system in a kind of an IoT device. And so you can imagine that we have these bits of hardware that we're shipping out to the edge, and we need to be able to push updates to them very, very reliably. And so we had a lot of performance and a lot of security and a lot of correctness concerns with this project. Other than that, though, I used to work a lot in Clojure and ClojureScript. These days, I mostly spend my time in Reason and Rust. But I am here today to sell you on Rust. And this is serious business. That's actually why I am dressed so nicely, so that you know that this is serious business. But I do have my button undone at the top, so you know I'm trustworthy. I'm kind of a chill business guy. So with that said, I've been practicing my pitch. Working with Rust in the beginning is like banging your head against the wall. I know we're all excited about that, but I want to set expectations at the beginning of this talk. It's good to think about Rust from the negatives initially. So you're at least setting expectations. Basically, anytime you have a bit of JavaScript code, if you write the equivalent in Rust, it will be longer, it will be more intricate, and will have a lot more symbols. It's not always true, but it's just a good attitude to have because it's true enough of the time. Now, Rust itself is described as a systems-level programming language that cares about performance, security, and correctness. I don't know if systems-level programming is such a good description for it, because it goes in a lot of interesting destinations. But that's how they describe themselves, so we'll run with it. But from a JavaScripter's point of view, Rust is interesting because it's low level, very, very, very low level, but it has a lot of abstractions. They focus a lot on zero-cost abstractions in particular. It also has guaranteed memory safety, which is a big issue whenever you are working in a lower-level language. It also cares a lot about concurrency, so it has threads without data races, and it has some nice things that kind of inherits some of the reason type of features, like type inference and pattern matching, and has a very minimal runtime. But why would you care? Why do you want to have low level but with abstractions? Rust is very focused on very predictable performance at any given time. It's going to give you as much control as you need to eke out every bit of performance from your hardware. This includes things like memory allocation, layout, garbage collection, all of that sort of thing. But once you get access to all of that power, basically you have this amazing gun that you will immediately point at your foot and pull the trigger. It's very, very difficult to ensure data integrity whenever you have this level of control. And in particular, trying to maintain any sort of data integrity with that level of control, with concurrency, is next to impossible. So many of the bugs that we face in our day-to-day usage of servers is because of threads with data races. And type inference. Type inference is a topic that's near and dear to my heart. But I would say, before we explain what type inference is for, why not step back and actually ask, what the hell are types for? And if you ask C, C says types are for performance. Types tell the compiler, for all of your data, how should it actually be represented at runtime, both in memory and on the CPU. And TypeScript and Flow, they don't care about the layout of the data. What they care about is correctness. Right, if you think about C, it can't prevent many of the mistakes that you might have where you pass one string when you should have passed an array. I mean, as long as they look like bytes, it's fine. And TypeScript, you can add as many types as you want, but it will never be used by V8 whenever you're actually running your code. So you kind of have these two different values that types might offer, And different languages will choose different pieces of it. And Rust says that, well, types are for correctness and for performance. Why not do both? And there is another language that has said this before, Java. I know Java is not very popular. And if you look at Java right here, so this is an example of declaring some variables in Java. And you say, hey, I have an integer called number, and it's 29. And I feel like this is like working with a compiler that's very hard of hearing, right? Because I say, hey, my flag is false. And you should know that it's a Boolean, right? What else could it be? I told you it's false. But the compiler's like, oh, I'm sorry, I didn't hear you. And so you have to kind of shout that it's, hey, this is a Boolean. And you have to repeat yourself a lot. So the idea is type inference actually says, what if the compiler were to look through your code and say, can I figure out the types for you? So in this case, I'm declaring a variable called elem, and it's going to be an element inside of my array. And it's just 5. The U8 is a literal for an unsigned 8-bit integer. You don't have to have it, but it's nice if you want to have it. And you see that I'm going to create a vector, which is basically an array. But I don't say what the vector is of. I just say, hey, it's a vector. And now whenever I push the element in to the vector, Rust knows this must be a vector of unsigned 8-bit integers. And the cool thing is that we have very, very minimal type annotations that a programmer has to do. But the compiler is still happy, right? The compiler can check for all sorts of bugs, and it can optimize the exact memory layout of your code as much as you need. And so the compiler is happy, and the programmer is happy. And it's kind of this principle in Rust where wherever possible, the computer should be doing work for us, rather than us doing work for the computer. Now, why is a minimal runtime so important? Right, so traditionally with things like C or C++, you're kind of targeting beefy machines, right? You're pushing to Linux somewhere, and it has gigabytes of hard drive and gigabytes of RAM. And it doesn't matter how big it is, right? Because you'll download it once, and it's fine. But as we start to push to smaller devices or to the web in particular, that puts a lot of pressure on how much data you can actually ship to your client. So Go is another language that has been working really hard at having really great WebAssembly support. The challenge is Go was originally designed to run on servers, where space and size are not a concern. We care much more about performance than we do about size. And so what that meant is that Go has kind of built this culture where, by default, a Hello World Go application compiled to WebAssembly will start at 2 megabytes. And if you pull in any library, it's going to balloon to about 10 megabytes very, very quickly. And I'll give them credit. There's work on a thing called TinyGo, which is a subset of Go that starts at 10 kilobytes, which is amazing. But the challenge here is libraries actually have to add support for TinyGo, because the ecosystem has built up with this expectation that, well, having a big runtime is not a problem. But Rust was originally designed to go everywhere, including embedded devices that are so small, they can't actually fit libc. So you can write a Rust program that will compile with no standard library. You have to bring your own. But that gives you the ability to define exactly the size and performance characteristics of your application. And like I said, Rust inherits a lot from the ML language of family, so like Haskell or OCaml or Reason. In particular, pattern matching. So pattern matching is near and dear to my heart. So you can see here that I have a list of greetings. So there are 3 of them. And what I'm going to do is iterate over them. And I'm going to get the index and the item. And now I'm just going to have a switch here, basically match. And I'm going to say, based off of this index, I want to print out a different greeting. So if it's 0, I'll print it in English, else Korean, or Swedish. And this right here is not too bad, right? We can look at like the list of 0 through 2, and we can see that, yes, there are 3 greetings there. But what happens when there's a third one? Right now we can verify it, but what if these 2 bits of data were actually apart in the code base? Then what will happen is this will crash. So what happens is Rust has exhaustive pattern matching, where it says, I have detected a case that you have not handled. And in fact, I will not compile this because it is guaranteed to crash if this case happens. And you can see here that it's giving me this nice error message. The error messages in Rust are heavily inspired by those in Elm. So it's a systems-level programming language that really cares about developer experience. And you can see that, hey, you didn't cover this underscore case, which is kind of a weird thing to say. What it's saying is, I looked at what you're mapping over. You're mapping over numbers. It's really hard for you in one source code file to list every single number possible. So you need to have a default case, which is this underscore. So it's literally telling you, hey, you need to add support for this default case. If it was something else, like, say, an enum that had maybe open or closed or some finite number of states, it would have said, hey, you have open, but not closed. You should handle that case. And the cool thing is they canonicalize all of their errors. So you can see here, if you want to know more information about that, you can just say, hey, Rust, explain to me why is this so important? Why are you bothering me about this? And it will actually print out documentation in your terminal or your editor saying, hey, here's a list of all the things that could go wrong that I'm watching out for you right now with this error. So we add a default case, and Rust is happy, and we're happy, because we know that this is never, ever going to crash. So from the correctness point of view, I would say debugging sucks. There is never a time that I'm excited about debugging unless it is so bad that I'm like, oh man, when I go to the pub tonight and I tell people about this, oh, it's going to make for a great story. But most of the time, I don't want to be debugging. So I would say there are 3 questions from order of easiest to hardest about debugging. The easiest is who should be doing the debugging. Second is when. And third is where. So who should do it? Well, this is easy. The language. By virtue of construction, the language should make it so that it is impossible for me to add bugs into my program. Wherever that's not possible, because the language needs to give me more power that might introduce bugs, the compiler should start checking my code. Right? The compiler has access to all of my code. It has access to all of my dependencies. It should be checking through everything that the language couldn't to make sure that I didn't add any bugs. And then maybe some automated tooling around like linters. Maybe this is something that my company has about some rules about how I should be coding. Finally, there are tests. If all of that fails and I have to still debug, then I guess it's me. But if a developer doesn't do it, then the user does it. And that's the worst scenario. Right? How many times have we been on a plane or train booking website, and you go to submit the form, and it doesn't work? And so you open up the console, you get the HTML element, and you manually submit it in the console, and it works. Right? So that it's possible for the user to debug, and maybe that's a good thing, but it's certainly not a great experience. And so the next question is then, when should debugging happen? And like Elm, Rust says it should happen up front. You should push all of that up front because the moment that you introduce that bug is the moment when you had the most context to fix it. So it's going to list out all of the bugs that you have at any given time and say, fix these before I compile. And that means that by the time you actually get it to compile, it just works most of the time. It's actually a very jarring experience, especially coming from something like JavaScript, which is amazingly flexible and a lot of fun to program in. But it will allow you to make mistakes that will take you a long time to track down. And I want to give one last shout out to the Rust community here, because they have built a crazy, empathetic, and welcoming community. Most systems programming languages, the community is not known for being very welcoming. But this community cares hugely about the experience of new developers and experienced developers. So much so that they regularly have surveys about the experience of different parts of Rust. And then they will actually take the top pains and form a working group. So they knew that WebAssembly was going to be a really important task for them. So they actually formed a working group to say, your job is to make it so that someone who doesn't know Rust can come to this website, read through the docs, and have a fully working game of life in 30 minutes, which is an insane task. But it is, they've done it. So now, why would you care as a JavaScripter? And it's because Rust now actually compiles down to WebAssembly. And WebAssembly is pretty crazy powerful. It is, I think, unprecedented in how well designed it is and how adopted it is. Usually, a lot of great technology kind of never gets adopted. I want to give another caveat here, though. Using WebAssembly from JavaScript is currently a little bit unidiomatic. It feels a little bit weird. But it's not too bad. But that also means that because Rust is compiling to WebAssembly, that'll also be a little bit painful. But in particular, Rust is compiling down to JavaScript, or sorry, into WebAssembly. And WebAssembly literally is just a big array of bytes, ones and zeros. There are no strings. There are no floats. There are just ones and zeros. And all the things that we take for granted in JavaScript don't really exist there. And yet we want JavaScript to be able to call functions and pass in data and retrieve data, more than just maybe ones and zeros. So what we need to do is figure out how to interop between these two systems. By default, your JavaScript will load up. It will reach out and download a big blob of wasm data. It'll instantiate it and pass in all of the functions from the outside world that the WebAssembly bundle is allowed to know about. And then having instantiated it, it can now call into functions that exist on the WebAssembly side. So you can imagine here that I have my wasm, and I call greet, and I pass in hi. That's going to go over to the WebAssembly side. I've implemented a greet function there, and I'm going to return a string back. But this bridge right here, going back and forth, has to be implemented by me. And when I'm implementing it, I have a couple of different goals. One is I want to minimize the copying. Because these are two separate worlds, they both have their own view of memory. Their memory does not touch one another. And so that means if I were in JavaScript and I just copied a bunch of memory and sent it over to the other side, that would actually be really slow. It would put a lot of pressure on the garbage collection. And it would kind of, in many ways, like defeat the point of using Rust, which is I want to have fine-grained control over memory allocation and performance. So what we're going to do instead is on the WebAssembly side in Rust, we're going to create a huge array of memory. And now on JavaScript, we're going to actually just call a function like, hey, Rust, can you create the game world for me? And this will initiate all of the, or initialize all of the data structures, the world, the players, etc. And then it will just pass back pointers to JavaScript side. And these are very, very small. And now JavaScript is going to just call functions using these pointers, and Rust will update everything. And then JavaScript will be able to just reach into the memory and see the result. And this is nice because JavaScript has so many things that we take for granted, right? Access to DOM, to garbage collection. Like, you have objects. Objects are cool. You have arrays and strings, like things that you don't feel are very special, but whenever you don't have them, you really miss them. Whereas on Rust, you have all this nice performance and memory management, but you don't really have objects. You have like structs, and you have arrays and vectors, and you have two kinds of strings for whatever reason. Rust people will say they don't. I will say they do. So what we're going to do is have this shared memory between them. JavaScript will call into Rust. Rust will update the memory, and then JavaScript can read that memory. So we have this nice cycle flowing, a bit like React, maybe. And that means that we can make sure that we only pass small bits of data between the JavaScript and Rust side. And everything is able to actually kind of exist inside of the uint8 arrays. But we still have to, on the JavaScript side, even though we can read all of those bytes, it's still unpleasant. We have to figure out how to construct strings and booleans and whatnot from them. But the Rust people are aware of this. And they have built phenomenal developer experience. So what I've done here, this is the game of life written in Rust. I have a cell, which is an enum. A cell in a game of life can either be dead or it can be alive. And I'm saying, hey, Rust, I want you to represent this as a 0, and I want you to represent this as a 1. The rest of the world shouldn't know, but I care about how that's actually implemented in memory, because I need that for performance or whatever. Now, every tick that gets called from JavaScript, I'm going to iterate through the entire board, and I'm going to get a list of all the neighbors around a cell. And now I'm going to match. And you can see this pattern matching again, where I'm matching off of 2 items, which is really cool. And I can say, hey, if this cell is alive and the number of neighbors is less than 2, then this cell should be dead, and so on and so forth. So in this one line right here, or this one chunk, I can concisely encode all of the rules of the game of life. It'll be type checked, and it will be immaculately laid out in memory. Now, what Rust is going to do, as part of this, as an automatic part, whenever it generates the WebAssembly code, it will also generate an npm package, so that you, on the JavaScript side, will be able to pull in all of those functions and call them. But not only that, remember that Rust is statically typed. It has intimate knowledge of all of the types in your application. So it will also generate TypeScript bindings. But not TypeScript bindings like I would write, where it's like, oh, it's any, I'll come back and fix this later. It writes them as though I were a really good programmer. So now we can come in here, and let's take a look at what this actually looks like with a real application. So there's a component library, or there's a library called U. And U is inspired by Elm, except that what it's going to do is you will have a JSX-like syntax. You'll have service workers that will get spun up in the background automatically to handle concurrency. And Rust is going to guarantee that you have data integrity, no race conditions, all throughout the entire experience. So you just write a normal Rust application, you compile it out, and you're going to get all of these benefits. So this is what it looks like to write a component using U. So you can see I have this HTML with a bang. This bang is really cool. Bang means this is a macro. It's like a Babel transform, but it's built into the language. So any library author can ship a JSX type of thing as part of their library. They can bring the language into their domain and make it much more accessible. And so this library has actually implemented their own HTML macro. And all of these props here are actually typed. So if you pass in the wrong type, or you have the wrong children, it won't compile. So this is like an amazing experience to actually write HTML inside of this low-level language and have everything typed and compile out nicely. But then we have maybe events. So imagine I have, in my core loop of my application, I have a request. So I'm going to send this off to the service workers, or they can send it to me. And the response to it should come back as an answer. What I'm going to do is, whenever I receive a signal, I'm going to match over that and say, hey, if the signal was a question, then pull out the body, and then send an answer to this saying, hey, that's cool. And what this is going to do is this won't compile, because the message might also be a response. And also, if I add, for example, maybe I have a question right now, but maybe I want to add a demand later. Then if I add that in, everywhere that references that will break. And I'll be able to go through and fix everything once, compile it out, and it will just work. Now, this is what it looks like if you're actually consuming the generated Rust from JavaScript. So right here, this import memory, this is the big bit of memory that we talked about that the Rust compiler generated for us. So we're going to pull that in, and then we're going to initialize it as just a big array of bytes. We don't really care. But from then on, we're going to say, hey, get the cell at this index. And if that cell is dead, then I want you to draw a dead color, or else use the alive color. And the thing I love here is this dead is actually the enum that we defined in Rust. So we don't care if it was 0 or 1 or true or false or A or B. It doesn't matter. We get to code as though someone were a really good programmer on the other side, and they gave us this really good API. And that's all generated based off of the deep knowledge that Rust has about your program. I'll give a quick aside about the syntax. I mentioned before that Rust is a bit more verbose, but it is also very heavy with symbols. So just be prepared. But the nice thing is they care so much about developer experience and onboarding that the error messages will oftentimes navigate you out. So for example, here I have foo, it takes a b, which I said is a mutable, unsigned 64-bit value. I'm being very specific about what I want here. And it's like, hey, you are trying to borrow a mutable value. You can't do that. Maybe you should try just removing the and mutable. And what happens is it guides you out of this problem enough times that you start to develop kind of a muscle memory about what is this symbol actually doing. So I want to give one demo of what this actually looks like. So this is an NES emulator written in Rust. And it is super fast, super cool. If we open up the developer tools and we take a profile, you can see that the animation, or sorry, each of these frames is tiny. It's incredibly performant. It's very good on my battery. It's in fact been running in the background for quite a while, and my battery is still doing fine. But the cool thing is, with Rust, you can also compile out that same application to a native application. So this is it running using SDL instead of WebGL. And this is Super Mario Brothers using the same code that's type checked. And you can run this on a desktop or a mobile, or you can compile to the web, as we saw with the other example. And then there are some pretty other crazy things that are happening. So in particular, this idea of WebAssembly, like I said, is crazy well designed. And someone has actually implemented a WebAssembly to Rust compiler, so kind of like a decompiler. And someone actually, there's a subset of TypeScript called AssemblyScript, which is how TypeScript people go to WebAssembly. It's kind of the non-allocating subset of TypeScript. And someone wrote a really cool Game Boy emulator in that. And they compiled it out to WebAssembly, fast and cool. But then someone took the WebAssembly to Rust decompiler, turned that into Rust, and then they took the Rust code and compiled it out to a native application. So it's kind of a crazy pipeline, but like the future seems very exciting. And I'm going to end on this note that I think that we are actually, Rust and WebAssembly represent an unprecedented opportunity in our industry. Because our industry only moves forward via secretion. If there is any abstraction or any implementation that is even a little bit successful, it never dies. To that point, I have a terminal in my computer. A terminal is an endpoint, like a keyboard, that talks to a mainframe, right? And my terminal understands crazy old escape codes, but that can never go away. We are stuck with it forever. And we're also stuck with like libc. And libc has caused unprecedented amount of good, but also tons of security issues. It has been very difficult to actually ship anything reliably with it. And WebAssembly and Rust mean that we actually have a platform that it's not in our best interest to ship all of Linux, all of libc to the browser. We need to have a new, smaller implementation of these things. And maybe we can do it in a safe language that's also fast and also correct. And that could be Rust. And I actually think that in the next 5 to 10 years, most of the JavaScript that we run will be written in Rust. I don't think most people will write Rust, but I think that most of the code we run will be. Like, who will actually write it? It's the people who really want fine-grained performance control, and the people who want safety, security, and correctness guarantees. And this is largely library authors, right? How, like, to what extent does the React authors or Vue or Angular have to go through to eke out all of the performance and correctness? And so they're under tremendous pressures to actually do this, and they need tooling that helps them. And I think that's likely Rust. And I actually think that WebAssembly and Rust will also end up going to Node, where you can actually pull in all of these implementations of great Rust libraries that are already compiled out to WebAssembly, and it will just work inside of Node. No more libsass compiling C++ nightmare. So here's my closing pitch. Working with Rust, at least in the beginning, is like banging your head against the wall, but at a very slight angle, so that every time you hit the wall, you actually make a little bit of progress. And at the end, you actually look back at this blood-stained wall, and you're kind of happy, because you built a thing that you didn't think was possible. All right, here are some links, but otherwise, thank you.